All right, so let's go over the lab again. This is the reaction that I carried out. Reaction of acetic acid and vinegar plus potassium hydroxide gives us potassium acetate and water. The nice thing about this reaction is it's 1 mole of acid reacts with 1 mole of base. So the mole conversions are pretty straightforward. When you calculate the moles of base, then the number is the same as the moles of acid. You're still going to show that in the calculations, but it's just a 1-to-1 ratio. Again, as I said in the other video, and I'll show you again here, and I'm going to give you some sample data. You're going to take the drops of KOH for each trial, convert it to volume of KOH because you have that conversion factor when I calibrated the pipette. Then you're going to convert volume to moles using molarity that you calculated for this solution. Then you'll convert that to moles of acetic acid, to molarity of the acetic acid in the vinegar, and then finally to mass percent, which is actually mass per volume percent. So again, I didn't do the titration the regular way. When you did a normal way to do a titration, you've probably seen this before. This is a burette. It's just a long tube that goes from 0 to 50 milliliters. It delivers a very precise volume. For instance, you can deliver volumes that are like 20.03 milliliters. It's very precise. With the graduated cylinder, I was only able to get one significant figure, but for the purposes of this lab, that's fine. But when you carry out a titration, you have your standard solution. So this would be where our KOH would be, and you would carefully deliver it through this valve here, drop by drop, into your reaction. So this would be the vinegar down here with some water for dilution and some phenolphthalein indicator, and you would the nice thing about this setup is you have a hand that's free to stir the solution, and then you can control with your other hand this valve here to carefully control the base that's added. So that's a normal setup, but I used the pipette. It worked fine. The data that I got, this is what you're going to need to fill out this data table. So here's the lab report that I have posted on Canvas. So just read the introductory material. It's pretty brief, but here's the reaction again. Talk a little bit about why we're doing this lab. This is the number you need to calculate, so you'll get that from this data here. You'll put that number here, and again, here's the information you need that's key for converting drops to volume. The pipette I used was calibrated to deliver 5.0 milliliters of KOH for every drop, for every 119 drops used. So make sure you use that conversion factor to convert each of these drops that you'll fill in here to volume, and then you'll convert volume to moles using this number, and then from here to here it's the same number, and then you'll divide this number by the volume of vinegar, but make sure you express that in liters, and then you'll average all 4 of those trials and report one number here. I have 4 columns, but just put one number here. Maybe I'll edit that and put it back on Canvas so you're not confused. But here's the data that you need to fill in this table. Again, for each trial, or for the whole experiment, I'm sorry, I made a stock solution, 2.0 grams of KOH dissolved in 50.0 milliliters of water. So again, you need those 2 pieces of information to calculate this. So I want you to calculate that. You show the calculation in this lab report. So you're not going to forget anything. It's all laid out for you, organized in this order. And then I have the pipette calibrated. I used 5.0 milliliters of vinegar. So that's what you'll put here in your data table, 5.0 for each one. Notice I put the units in the row headings, so you don't need to put units in here, just numbers. Make sure that you have the right number of sig figs expressed. Here's the numbers that you'll just repeat or transfer to that other data table. I did this first calculation for you. You can do the rest. But again, I use the same volume of vinegar each time. That's what you do. And then you run several trials because you don't know if trial 1 was, you don't know if you overshot the equivalence point or not. So you run a few trials. You can see the numbers are all kind of close. So I multiplied, for instance, this for trial 1, I multiplied 163 drops times 5.0 milliliters over 119 drops. and that converts, this drops to a volume. 6.8 milliliters of base were used. That's where I got that number from. You do that for the other 3 trials, just using this conversion factor. You can complete your data table, and again, you'll fill this out. Everything I just gave you in that table will allow you to fill this row in, this row in, this row in, and then the rest is calculations you'll do on the next page, page number 2. You'll do all these calculations, and then you'll fill in your answers for these here. Now, I don't need you to show how you got every single box in this table. Just go through and show me for any one of these trials. It doesn't matter which one you pick. Just show me how you got these numbers for one trial alone. And because there's not room and it's not necessary for you to show me the work for every trial. So I specify that here. For questions 2 through 5, show sample calculations for any one of the above trials. For full credit, make sure you show your work, etc., etc. This calculation you just do once. That's using that data here, the 2 grams in 50 mils of water. Convert that to a concentration, and then calculate the volume of KOH used. That would be this type of calculation. Just show that for one trial. And then calculate the moles of KOH required to reach the endpoint. I'm going to give you some sample data here to show you how to do this, and finally that. Well, actually not that. That's just the average of your 4 trials. I think you can do that. That's pretty simple. I hope you find this overall easy. If you have any questions, just send me an email. I'm not hearing from anybody, right? So I guess it's okay. This part is a little tricky. Convert the average molarity to grams per 1 milliliter. We're doing that so we can actually convert that to a percent. So steps 7 and 8 in your lab report, again, we'll show you here in a second with some sample data. And then I have some post-lab questions asking you about does the calculated value of percent acidity that you calculated here agree with the label, 5% on the bottle. I want you to think about what sources of error I could have made that would cause this number to not be what the bottle says. Think about what I did, what you would do if you ran this lab, where mistakes might be made, and that would cause the molarity and eventually the percent to be high or low. And then I ask you about a question about why adding water isn't important overall, why it doesn't matter, and why is it better to titrate to a pale pink endpoint instead of a dark pink endpoint. So these don't have to be long answers. The space I give you is more than enough to answer those questions. So let's go through some sample data. Let me just make sure I've gotten everything explained in the lab. Again, this will be due not for over a week. 6 p.m. a week from tonight's Sunday night, early Monday morning. So a week from Monday at 6 o'clock. That should give you plenty of time to review the chapters on acids and bases. And there's a little section on titration in the other textbook, so you might want to review that as well. Okay, so let us go through and with some sample data. So again, these aren't the numbers I got. This is just, they're close, but this is how you'll do the various things that you need to do. So for instance, I made a stock solution. Let's just say I used 2.6 grams of KOH. I would need to convert that to moles. And this could actually be done in one step. If you want to show this in one calculation, you can, but I'm just breaking it up into pieces to make it a little easier to digest for you. 2.6 grams of KOH times 1 mole over 56.1. That's just converting this to moles. This is the molar mass of KOH, 1 potassium plus 1 oxygen plus 1 hydrogen. I want to see at least 1 decimal place for molar masses. 2 is even better, but a 1 is okay if that's what you choose to do. So this would give me 0.046 moles of KOH. Again, I only can report to 2 sig figs because this mass I used only has 2. I dissolved it in 60.0 milliliters of water. Let's say I did that. What's the concentration of my stock solution that I'm using? And remember, the stock solution is what goes into the burette. That's what you know. You know the molarity of this. You can control how much volume you add. You can control how much volume of vinegar you're using, but you don't know its concentration. So that's the fourth variable in that equation that you're calculating. All right, so back to the sample data. Here's what I would get for my stock solution. You can show this with the actual data. 0.046 moles divided by 0.0600 liters. Carry through all the sig figs and show 2 here, 3 there. Those zeros don't count. Those are significant. I get 0.77 moles per liter for my stock solution. So let's say for one trial, I'll just show, let's say trial 1, I used 171 drops were needed to reach the pale pink endpoint. Remember, at the pale pink endpoint, you are at the point in which you've just neutralized. When it turns pink, you've just gone a little bit past the point at which moles of vinegar that were there, or moles of acetic acid in the vinegar that were already there in the bottle, were completely neutralized by KOH. That's called the equivalence point. You go 1 drop past that and the solution turns pink. That's called the end point of the indicator, where the indicator turns pink, and then you know, oh, it's done. And that's what you have here. You have a solution of potassium acetate in water. But for each trial, it might take a slightly different number of drops. It's not always going to be the same. That's called experimental error or random error. But anyway, I convert the drops to volume this way. Here's my conversion. Just show this for any one of the trials, these calculations. And then I convert this to liters. So here's how I start now, converting this to molarity of acetic acid. It's a series of 3 calculations. So 7.2 milliliters I convert to liters by dividing by 1,000. I want you to show me this with all the units. Then I multiply by the stock concentration. That capital M, remember, stands for moles per liter. So milliliters cancel, liters cancel, because that's moles per liter. I'm left with moles of base that were needed. Well, I convert that now to moles of acetic acid, this compound. It's a 1-to-1 ratio, so the moles of acetic acid that I actually get are equal because the reaction is a balanced reaction, 1 mole of each. Then, one more step. Take that number of moles of acetic acid that were present in the amount of vinegar that I measured out in 6.0 milliliters, and I convert that to liters, and I get 0.0060 liters. I divide this number by that to give me the concentration or the molarity of acetic acid for that particular trial. You'll do that 4 times. You'll average those 4 numbers, and then you'll come up with the average molarity that's shown in this row here. So again, you can just write the number once for average molarity of these 4 trials. Write it here if you want to, or right in the middle, it doesn't matter. You don't need to repeat it 4 times. But what I just went through there was just showing you how to go from here to there, to there, to there, to there. So just show me any one of those trials in complete succession. The next thing you got to do in the calculations, if you look on number, number 7 says, convert this average molarity to grams per 1 mil and then grams per 100 mils. So let me show you those last 2 steps here. So once you get your average molarity, let's just say, for instance, that this was my average molarity. So 0.92 moles per liter. Now what I need to do is to convert moles to grams, I need the molar mass of acetic acid. You can look it up or calculate it. It's 60.05 grams per mole. So 0.92 moles per liter of acetic acid times 60.05 grams of acetic acid per mole. The mole unit cancels, top and bottom. I get grams per liter, but I want grams per milliliter, so I add this conversion factor, cancel liters with here, and just divide it by 1,000 to get grams over milliliters. And in this particular case, I would get 0.055 grams of acetic acid in a milliliter. Now I need to convert that to grams in 100 milliliters. Why am I doing that again? Or why are you doing that again? Because the bottle is expressed as a percent acidity. That's out of 100. So instead, we got to know how much acetic acid there is in 100 milliliters. So all you got to do is take that number and multiply it by 100. Show me this. And you're just moving the decimal 2 to the right. So you actually get 5.5 grams of acetic acid in 100 milliliters of solution in vinegar. So that's really a percent. This is the percent of acetic acid in the vinegar. To 1 sig fig, it's 5 or 6. The bottle says 5% on it. So I'm not sure what the data that I generated is going to give you. It's probably going to be a little on the high side, I'm guessing. I haven't done the numbers yet. But you're not necessarily going to get 5% for your percent acidity. So, but that's what happens in real lab experiments, especially when you run them in the way that I did. It wasn't exactly high tech. I was using a plastic pipette instead of a burette. So again, watch this. After this video, I have 2 other videos, 2 or 3, I think. I'll put right after this on Canvas. Watch those, and then that'll give you more than enough information to complete the lab. Please email me with any questions, and good luck. And I guess later in the week, we'll get into organic chemistry, so I'll have some videos later in the week, probably not till Thursday or Friday.